Okay, if the electric meter started measuring the current or the power and it realized that it was going to start getting into peak current, and you had all these different devices in this hospital, what could we start load shedding by turning off? And all we had to do was put like a little, I think you have one of those little ice cube relays, put that in series with the control circuit and control it with a separate control circuit. So here I have a control circuit from a computer controlling the ice cube relay that made and break the contacts to the control circuit. So here's a control circuit controlling a control circuit. But we were able to do that with very small wire. Well, the problem is I went to this hospital. All the air handlers were not on a 2-wire control circuit, but were on a 3-wire control circuit, which we'll talk about in a second. Now, a 2-wire control circuit means that when you lose power, it goes down. When power comes back again, they automatically come back. On a 3-wire control circuit, when you lose power, everything goes off. But when power comes back on again, you'll see that the loads do not automatically come on, but you have to somehow take some other action to turn them on. So you can imagine how inconvenient it was for this industrial facility, this hospital, that every time they lost power, maintenance had to go around and press all these air handlers to turn them all back on again. So there's an in application. So 2-wire control circuits, it's great because you lose power. When it comes back on again, everything will work fine. The motor will run if that's what you want, but maybe that's a safety hazard. Can you give me some other examples where it would be a safety hazard for a 2-wire control circuit?
Well, maybe not a safety hazard, but if you're buying your power with peak demand, and if you have 100 motors that all come on at the same time, you can really mess up your peak demand and get penalized.
Good point. So you want to be able to stagger things in some way.
Well, going back to your safety hazard, if your overloads trip, you'll be standing right in front of that breaker when you reset them. So if it's 2-wire control and it's still turned on, you may want to make sure it's off before you reset your overloads.
Gotcha.
Good point.
Caution, the terminal numbers found on a schematic won't always match up with terminal numbers found on some wiring devices. Wiring must always be based on the function, not the terminal numbers. All right, we have number here. You might have seen throughout the textbook, we got a number 1 here, and then we got a number 1 there, and then we got a number 3 there, and then we got a number 3 there, and we have a number 2 there and a number 3 there. In some cases, this is probably a number 2, and this is probably a number 3, but we got to be careful that there is no universal numbering that, okay, just take from this number, it's going to go to this number, because these 2-wire control devices have no numbers at all. So the numbers that we're using is just a way for us to communicate in the textbook, communicate in the video, that you can see, okay, that goes to there. That's no more than that. So we're just using these numbers for convenience. So you're going to have to know your devices, understand the application to make those proper connections. Optional wiring. Schematic often indicates optional wiring by using dashed lines with instructions. All right, let's see what we got here. We have this particular, will show us, okay, you can take, let's go here. All right, line 2 goes to the overloads. Okay, that side of the coil is taken care of. We're not going to worry about that. This wire here from the side of the coil going over to number 3, if that were number 3, that's automatically done by the manufacturer. So, I got a float switch right here, and right now I set it up so that it's a normally closed, so if water or the liquids rise, this is going to allow, the way it's set up, the way it's set up right now in this part of the circuit is that when liquids fill in, it'll stop. This allows water or liquids to enter. But it shows the optional, well, if you want to, you don't have to connect it to the normally closed float switch portion. Connect the normally open, that would allow liquids, that as soon as liquids rise a certain level, it would, one second, is there a difference? This one allows it to come up and then stops it. Oh, okay. This one, all right, this one purposely keeps the motor contacts energized to have maybe liquids come in and then stop. This one is liquids might be coming in through some other source, and then it would close the contact. If you use the dotted line, you got rid of the top portion, then you'd energize the coil. Did I mess anything? Did I make it clear, or did I make it worse? Let's try this again down here. All right, line 1 comes over here. It's a normally closed contact. Guess what? This motor is running because it's normally closed. If this float rises for whatever reason, well, then that coil, rather, is energized, the motor is running, the coil will be de-energized. If I go with the optional method, which means I get rid of this section here, then since it's normally open, this coil is not energized, main contacts are not closed, motor is not running until the float switch is closed. So this gives us the option. It's kind of like normally open, normally closed that we talked about earlier. You know, which way do you want to use it? What do we got here? I guess we're repeating. Okay, this is close, energize. When a wire is used on the normally closed contacts, the circuit will be can be used to automatically fill a tank. So normally closed contact, the water rises, levers, stops it using the A wire. And we come off of line 1 over to the normally closed. Another showing it. Pump is running. F float switch contacts are closed when liquid level drops to a certain level. Float switch contacts open when liquid level rises, turning on that motor, turning off that motor. Kind of being somewhat repetitive, but that's okay. All right, what about if I don't go with A, but I remove A and I go with this portion? Well, now it's normally open. That means that the pump is off until the water comes up. Then it closes the contact. I think we have it right here. It's off. Coil is de-energized. If the water rises, it closes the contact. Now it energizes the motor, possibly to have that liquid be removed. 3-wire control circuits. And this is one of those, it's automatic. It goes up, it turns on, turns off, it turns off, it turns on. It lose power, some power comes back on again. It's just going to go back to its normal sequence. There's no requirement to get involved. And it's kind of convenient for most applications. 3-wire control circuit just changes a little bit. It's used where the automatic restart of equipment, it's used where, 3-wire circuits should always be used where the automatic restart of equipment after power loss presents a danger. We don't want the equipment to come on if we lose power to restart it. A basic 3-wire control circuit consists of 3 control wires, kind of obvious, 2 momentary contact push buttons, one to start it and one to stop it, 1 set of auxiliary holding contacts. Now, this is the first time we're going to start using the auxiliary holding contacts that we've talked about multiple times. All right, let's take a look here. Line 2, the yellow, is already pre-wired. That takes care of one side of the coil. It kind of goes right through the heaters, takes care of that one side. If we can get power to the other side of the coil, well, then the coil is energized. So we come off of line 1, right here, and we go over to a stop button, which is closed. Then we take that and go over to a start button. And the start button is normally open. And it also takes power over here to this normally open contact right there. And we're going to talk about what happens when you press start. You know, looking at the pictorial, it's hard. I really like the ladder diagram.
Oh,
My
exactly.
gosh. I thought I liked the pictorial, but you really can't understand because here's normally open over here, normally closed here, here's normally open here, but you don't realize that this normally open is in parallel with this normally open over here. You know, it's hard to see that where if we come over here, okay, I got my stop button, line 1 to stop, which is closed. Then I go to the start button, which is in series with a stop, but it's open, momentary push button. And then there is the M contacts, and this is the auxiliary contact, which are right there. There's your auxiliary contact, open. Here's your start push button, open. Here's your stop button, close. Stop button is a series with the start button. This is closed. This is open. This M contact is in parallel with the start button. And let's look at the wiring diagram here. Let's take a look at this one. All right, I come off of line 1, I go to stop. Well, this is not too bad. I go to start, and the start wire goes to one side of the auxiliary contact, and then on the load side of the start button, which is momentary open, momentary close here, I go over to 3. All right, I understand that. Eric?
The nice thing about the designation of terminals 1, 2, and 3 here is that the 1, 2, and 3 are the same for all different diagrams. So it's
Yeah.
easy to go back and forth and see which point is which on the different diagrams. So it's a real good teaching aid.
So by us using some numbers, we can all kind of get to point 1. As
Yeah.
you know, we can all go to point 2. What's the voltage point 1? All right, so now let's work some examples. Here we go. I got power now going to line 1, goes over to the stop. It goes over, supplies one side of the start, supplies one side of the auxiliary contact. Now let's take a look at this part right here. I'm going to stop right here. I want to go, it's right here and there, or here is through the stop, and now I'm supplying this start, and power is coming over here. Is that right? So this is energized to this point. So point 1 has power, point 2 has power, and this auxiliary contact, which is in parallel with the start button, I'll call it line, has power to it, or has voltage. Not power, voltage. All right? Then if I press the start button, well, now I have voltage going to the M coil. Let's go back and take a look at that. If I press the start button, I now have voltage to terminal 2. I will put voltage to terminal 3. Voltage will go over to this point right here, which is connected to the black wire, which gets me to the coil. When I press the start button, I am getting voltage to the coil. When you energize the coil, it will close all 3 main contacts to the motor. When I press the start button, I energize the voltage and get the voltage to the coil, energizes the coil, close 3 main contacts. These T1, 2, and 3 is energized, and this auxiliary contact, which is connected to the same coil, reactive, that contact that was open now will be closed, and the one that was closed in the auxiliary contact will be open. So I press the start button, energize the M coil closes the M contact. This is all, in this case here, just as I'm holding it. Then when I release the start button, I have voltage traveling from 2 through the closed M that was normally open to now held closed M coil, energized in the coil. And that's called the holding circuit. Isn't that a latching circuit also? Or an interlocking
Holding
circuit?
contact.
You know,
Correct.
holding
Memory.
contact?
Right.
Memory circuit.
Memory circuit?
Or CLN.
Ceiling.
Sealing it in, whatever the trade guys are going to call it. So let me go back to this again. All right, right now the coil is de-energized. M contacts are closed.
Open.
M contacts are open. Press the start button. Energize the M coil. Close all the M contacts. Main motor contacts are closed. Motor starts. This M contact that was open will close. Take your finger off, and using the holding contact, the interlock, the latching, the auxiliary contact, that coil keeps that M contact closed, which allows now that motor to continue running after you release the momentary start button. If we lose power at this point, or if we press the stop button, either way, we de-energize the coil, and that opens that normally open M contact that was being held closed, resulting in all M contacts opening, coil de-energizes, motor starts. Back over here, if we were running and we lose power, then we're going to end up being in this state right here. The motor will not restart. You have to manually go in and press the start button. Now, I don't know. I live in a rural area and we lose power all the time. I don't have a factory there, but I know there's factories in our community. They lose power all the time. So I can see this could be a problem where you're worried about safety because you want to make sure that if you lose power, it turns off. But do you have like a lot of buttons that you got to go around push every time? Do you lose power a lot, Dan? I mean, is it?
We lose power from time to time, but the safety factor is that there's a lot of equipment that you wouldn't want to restart when you get power back. You would have to clear out conveyors or make sure that the next step is ready to accept what you're going to give it.
So if you lose power and you have this assembly process and conveyors and everything all tied in together, you don't want power to come back on again and everything is normal. You're saying, hey, when power comes back on again, we need to now take everything off the assemblies. We got to start this one process first, get that going, then get the next one going and get the process that we know is going to work the way we need it to work.
Yes,
Because
we need to restart everything in the proper sequence.
I like that, in the proper sequence,
Right.
not just start going around pressing all the start buttons throughout the facility. Eric, what about you guys? You Dow Chemical. I mean, you guys must have thousands of push buttons.
Yeah, we also have process computers, but that's really the least of our problems, or the least of the issues. You have a power failure, something comes down, that's a major issue. Because if you start a motor before the process is ready for it, you could overpressure something, a pressure relief valve could blow, and you could have a loss of primary containment. So you have to, as Dan said, start things in the proper sequence.
So I guess then in your case, you're concerned about power quality in the sense that you want to make sure you don't lose power. In other words, number one thing is don't lose power, because the startup sequence, just losing power for a second could take you a long period of time to start the whole process to get to where you were when you lost power that instant. Am I right about that?
It could easily take a day to start something back up.
Just to get everything back to where
Right.
1 second down, we got a day trying to get it all up and all the. And I guess there's a lot of tension as to whether or not everything is being started in the right sequence and everything is going correctly until it gets going again. So I can see there's a lot of tension there. But safety. All right, let's go on. Wire diagram for a start-stop station. A ladder diagram and a start-stop push-button station labeled with numbers shows where the control conductors are connected. And that we talked about this. And arrow lines indicate connections made by the installer. Plain lines without arrows are also used. So these numbers are not universal. They might be common to some manufacturers. So you're going to try to be careful you control that you make the connections according to maybe the numbers on the manufacturers, or make sure you have to check your continuity tester, make sure that's a normally closed, that's normally open, and connect these devices. Is it a problem? Because I don't do controls, But if I went out there, started to go out and do controls, am I going to have a hard time? I would have liked to see numbers, and you're telling me the numbers aren't always the same. If I was hooking up a 2-wire control circuit, I don't have to know the numbers. Is that right? I just got to get off of line 1, and then I got to drop it off on the other side of the coil. So that's a pretty straightforward thing. If I'm doing 3-wire control circuits, just 3-wire control circuits, are the numbers pretty much on the auxiliary contacts and the contactor that a 3-wire control circuit, these numbers that we've been talking about are okay?
I wouldn't say so.
Okay.
You just wouldn't ever trust numbers. The numbers are great for this
I got you.
graphic right here, because you can see in the 3 different diagrams where each terminal is. But what you have a big problem also out in the field, that let's say that your equipment needs a momentary push button, and yet you have a maintained switch. And sometimes you think, well, wait a minute, I'm wiring up a maintained switch, but the equipment needs momentary, and you run into these kind of issues all the time.
I want to put this in practical terms, because, I'm sure a guy can watch a DVD and he can read a book and he can answer the questions in the unit. But I'm more concerned about how hard is it somebody who doesn't have somebody he's working with to be able to do controls if you just watch the DVD and you read the book and you get these devices. Would you have to get a continuity tester to check these things? This is not... I mean, when you have experience and you got the same product, same manufacturer, it's like you've done this enough times, it's intuitive. But what about a person who hasn't done this enough time? Is this something that you really need to pay attention?
Yeah, it's something
think
you
so.
really need to pay attention. And most of them are marked normally open, normally closed, so you'll have that.
Okay.
Some of the discrepancies come in with the type of equipment you use, like we talked about NEMA starters. Most NEMA starters will have 2 and 3, will be pretty consistent. But IEC starters, like the one we have right here, we already talked about, its auxiliary contact is number 13 and 14. So different brands, different manufacturers may have different numbers. But the normally open, normally closed, you really have to pay attention to that part.
Well, I think, Mike, also if you take and you actually do like what you said, take a meter, and actually start, physically connecting, put your meter on continuity, and just go through.
You need
the
to do
contacts
that.
without being energized. Go through the contacts and close it, manually close it, reset it. Just figure out how this thing functions without having to tear it all apart. And it's going to make a lot more sense that you're going to find the normally open contacts, you're going to find the normally closed contacts, so it's
Okay.
going to click a
So
lot easier.
I really like what you're saying there. So if you haven't had experience, you're going to get your continuity tester. You're going to find, okay, goes here. Okay, oh, I see. That's line. Okay, that's the overloads. Okay, that's the auxiliary contact. That's closed. That's open. I understand how this works. I know that all I got to do is get voltage to one side of the coil. I'm going to tap off a line 1. I'm going to go somewhere and do something with it. And if I can somehow bring voltage to the other side of the coil, that coil is going to energize. Those main contacts are going to close. Now, what happens when it happens? What happens after that? Then we need to follow the logic. Okay, what do I want? Well, I want that when somebody opens this, that I want the motor to come on. Well, then it's a 2-wire control circuit. And when they do that, okay, that's just contacts. No, I want it because of safety. I want to make sure that if we lose power, you have to start the process. So as you take, I think one of you guys said, it might have been Dan, that you layer. You do one thing. What do you want to get done? I want to be able to start this thing. Okay, then let's get that. I want to be able to stop it. Okay, well, then we need to add a series stop button. Normally, it's a normally closed, momentary open, or whatever the case, depending on the circuit. So I can see, personally, you gave me, Dennis, okay, yeah, I can physically get this. I can check this. I can check my devices. I can get a piece of paper and draw out what I'm trying to achieve. And you know what? If you can't draw it out to what you're trying to achieve, I guess what I'm picking up here, don't start screwing around with pulling any wires and making any terminals. Am I right about that?
Yes.
I mean, you need to get, okay, I got my contactor or my starter, and I need to be able to know exactly what's there. I got my devices. I need to know what I want to achieve. I need to be able to draw this out. Like I've said, to me, I believe somebody doesn't understand something if you can't explain it to somebody else. If you can't explain it to somebody else, then you don't understand it. And you should be able to explain it to somebody else who doesn't have your knowledge. And you should be able to break it down into simpler terms, basic elementary concepts, making some kind of relationship to something else. And if you can't do that, then you really don't understand it. So if I can't sit down and draw the circuit out on paper, then I need to get with you, Eric. Hey, here's what I'm trying to achieve, and here's what I think. Or get with you, Dan or Steve, right? And be able to draw this thing out and understand it and be able to see the continuity tester and say, okay, now, before I wire everything, I get my start button, I get my stop button, I get my contactor, put it together with a couple 18-gauge wires just right here on the table, right? Like on a lab, in a classroom. And then, okay, take voltmeter, 2 guys. Okay, here, I'll press the button, I'm checking. Oh, yeah, that would be there. Okay, I see how that's going to work out. That's what would give me the confidence. Then it's like, okay. So if I had a garage door opener, I'd want to do the same thing. I need to know it until I gain the confidence to how to work it. So hopefully this will help you learn to be able to draw it out, like we showed on, on a piece of paper, hand-drawn. Understand your equipment, your contacts, the switches. What are you trying to achieve? How does it work? All right, and we learned numbers. It's great for the book. It makes it easy, but that's not the way it's going to be in the field. Well, let's move on to low voltage protection. Low voltage protection only applies to magnetic controls. Let's see, what is this right here? Built-in low voltage protection of a 3-wire circuit. All right. Apparently, the start button has been pressed, so we have voltage across the holding contacts or the auxiliary contacts. The coil is energized. M contacts are closed. This M contact's being closed. Everything is running fine. If I lose power, then I have 0 volts at the coil. Then the auxiliary contact opens, and so that's the end of it. Power comes back on again. Well, it comes back on again, but the process can't start, and that's where that low voltage protection, where the safety comes in. I'm not sure about low voltage protection. If that's the right word.
That's the correct term.
It might be an industry term.
It's an industry term.
To me, I'm thinking low voltage protection of the motor, not protecting somebody from it restarting. But if that's the industry term, that's what it is. So what do you do if you lose? Let's go back here. It runs. Everything is fine. Power disrupts. No power at all. We had no voltage there. Power comes back on again. Well, the problem is, yeah, you got voltage to one side of the coil, and you have voltage coming to your start button and your M contact, but we can't start that motor, we can't start the process until we energize that M coil again, and that only can come from press and restart. And that's called low voltage protection as an industry?
The reason, Mike, that it's called low voltage protection is because the coil, the M coil, will drop out at a certain percentage, say 70%, 60%, whatever. And so when the voltage gets to that point, the coil drops out and protects the motor from running at a voltage even lower than that.
All right. So we're talking two separate things here. We're not talking about safety, even though a 3-wire control circuit is when you lose power, it doesn't restart.
Right.
I mean, that's just, we talked about that earlier. This is like, no. If we come back over here in this original example, if this voltage dropped down to not 0 volts, be this same power disruption, if it goes off, you're not having any low voltage protection. But if this coil was operating at, let's say, 190, and that coil doesn't have enough voltage to operate, well, that means, guess what? Your motor doesn't have enough voltage to operate. Mm-hmm. That low voltage protection is that the lower the voltage, there's a threshold where the coil drops out.
Right.
That's going to protect the motor. And then when power comes back on again, well, it won't really matter because you have to restart it for safety applications, but you're still going to go back to the same procedure that once you restart it and you go back to the whole sequence that takes us back there, if that voltage goes down, that coil is going to drop out, open up the circuit, and we're out of the game.
And then in the 2-wire control, they call it no voltage protection. There's the 2 industry terms.
Hold on. Well, if it's 2-wire circuit, you still have low voltage protection. No,
you call it no voltage. You got to have no voltage before it's going to drop out.
Why would wouldn't a coil drop out at 2 wires? Whether if the low voltage is low voltage.
Yes, you're right, Mike. It will drop out, but it won't stay dropped out.
It'll chatter.
Right. Let's say you have a brownout for a certain amount of time.
Now here's an example. I've seen this happen. All right, a motor starts, 2-wire circuit. When the motor starts, it starts drawing current, so what happens to the voltage? The voltage goes down. Well, it gets down below the coil because the coil is being connected onto the motor circuit. Well, now the voltage goes down. Well, because the voltage goes down, then it drops out the coil, a 2-wire circuit. Well, now the voltage dropped out the coil, it dropped out the motor. Well, what happened to the voltage?
Goes back up.
Well, the voltage goes back up again because you dropped out the load off of the circuit that you tapped on, which was the motor.
Yeah.
Well, all of a sudden the motor starts again. Well, then the coil kicks in the contacts and the motor starts to run again. But all of a sudden, guess what? Well, now it has under voltage because the voltage dropped. Then it goes back and forth, back and forth, back and forth. So there is no voltage protection. And I understand that concept. I'm trying to tie in these industry terms with the logic that it approaches. So we have no safety protection on a 2-wire circuit, right? Because it restarts. A guy could be, I mean, how many times have you guys read in newspapers where this happens a lot in concrete plants and people get into drums all the time. And this power goes off and a guy figures, oh, well, you know, power's off, so now it's time to jump inside these concrete things and they start beating all the concrete off the inside of these tubs and all of a sudden power comes back on again and the guy's inside this great big grinder and all of a sudden the guy gets just all chopped up because it was a 2-wire control circuit. 3-wire control circuit would have prevented that from happening because you can't start that until you press the start button. Plus the 3-wire gives you the ability that once you have low voltage and the coil drops out, which protects the motor, well then the motor's not going to restart again until you manually go back in again. Anybody have any comments on that? No? All right, let's talk about some exercise for reading wire diagrams. And I think we've already done this, but I'll just do it one more time. Okay, line 1 here is the line side of the stop. That's the wire coming in, point 1. Okay, I got that there. And then this is the load side of the stop. Okay, well then that would be that point right there. And then the load side of the stop, so we have line 1, and we go to 2. 2 supplies the load side of the stop and the line side of the start. So 2 is the load side of the stop and the line side of the start. 3 is common to the coil and common to the load side of the start. So 3 is common, it goes to the coil, which we can't see, but it goes to the load side of the start, helping us kind of like just kind of tie together there.
It's kind of like the hand-drawn diagram, because you know if you have a stop station, you need to connect it to, or you look at your line diagram, you know that you have to connect the load side of a stop switch to the power supply.
I guess this is a mental point, is that right?
Yes.
Mentally, you're saying, okay, that's there.
It's like you could
that's
do this without
there,
the numbers.
That's there. Yeah, okay, without the numbers.
Kind of.
Kind of like, well, that point is there. All right. Multiple start-stop push buttons. That was Mike Corbett jumping in on there. Additional start-stop stations can be added to a 3-wire circuit. Let me tell you something. I can definitely hook up a 3-wire circuit right now. I'm not saying I'm getting sick of it, but I'm getting really close to being sick of this 3-wire circuit right now. I think I like the 2-wire circuits, but I can hook up a 3-wire circuit with auxiliary contacts and understand how the overloads work out. If I see another 3-wire circuit coming up here, I hope we can get off these 3-wire circuits. All right. All right. I want to add some multiple stops and starts to a 3-wire circuit. I know the advantages of them. Well, if you put a stop button in series with the whole process right here, then any stop button would obviously drop out the voltage to one side of the coil, which drops out the coil. Put the start button in parallel to the multiple start buttons. Any start button would get voltage to the one side of the coil, and the other side is already there, which would energize the coil. And you're saying, well, numbers don't mean anything. Understand the process. Know you're connecting things in series if you're trying to stop it, connecting things in parallel in this application here if you're trying to start it. I got it. Okay. Now, how do we actually really do this? How do we run the wires? What do we got here? We got disconnect. 3-phase conductors going to the motor. To the starter. 3-phase conductors leave the starter, traveling down to the motor. T1, 2, 3. Got it. Now push button. I'm picking up my control conductors, apparently tapping off the line side of the contactor. So I'm running 3 wires. So 3-wire control. Let's see what happens here. 1 wire goes over to the one stop, and the stops are connected in series with each other. Then I supply the one start, and I continue the one start. The other start. So we're providing power to both start buttons, and that's the number 2. And number 3 is any one of these start buttons would give me power to 3, and 3 I know is the coil. 2 is the auxiliary contact. I can visualize that. So this is what you'd have to do, draw this out. And even if you draw it out, then you have to then test it. Push this button here, follow how the currents travel as we show the different circuit.
Well, and here's the thing, Mike. If you go back to the previous slide, you have your ladder diagram. And typically this is what you're going to get from the architect or the engineer. And then when you get out there to the field, you go to the last slide that we're at, this is what you see out there in the field. You've got your start-stop stations, and one's 25 feet away from each other, and you got to run this conduit between the junction box and the start-stop stations. Then you've got to run your conduit from your disconnect to your motor starter, which is another 50 feet, and then your motor starter's 25 feet from your motor, and your start-stop stations are 50 feet from the motor, and so everything's all over the place. And you get all this wire out there, and you get it pulled, and then you start scratching your head going, this doesn't even look like my ladder diagram, because the physical relationship of what you see here on the ladder diagram is not the same than what it is in the field. And so you've got to start to be able to put all that stuff together and go, oh, now I've got 200 feet of wire pulled, and now I see what's going on and how everything's functioning.
Well, you know, when I was an electrician, I enjoyed pulling wire. I can't explain why. I love circuitry. I love with the combinations and where you can drop off these wires here and continue these. I love not making splices, pulling wires through whenever possible. That was just, I just found that to be a challenge. And you had to really think ahead. What were you trying to accomplish? What wires and what colors? Because color coding was important to me. If this was going to be a switch leg or if this was going to be a feed, if I wanted to drop something off here, did I want to put a loop here? That would I run through that there? What was I trying to achieve? And you had to really think this thing out and how you were going to do it in advance and how did you run the pipe? Well, you had to know how you wanted to pull the wire before you ran the conduit. And then you ran the conduit, and then you had to visualize and know, okay, I'm pulling the wire, got a snake, I had snake in both ends. I'm pulling this one, I'm pulling that one in there. I had to know, okay, this one, drop off the 2 colors here. Okay, pull these other ones through. Okay, pull these back here. Boom, 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 and then you get it back. But I was able to visualize in advance before I ran the conduit, before I pulled the wire. Good point. Steve, you going to say something?
I was just going to say, and if the engineer doesn't give you a riser diagram like this, and if you're just working from a line diagram, this is where you're going to have to do your hand drawn and come up with that riser on cardboard out on the
Right.
job if it hasn't been done.
I would have to do this on paper. There's no question about it. I would have to draw this out on paper, and just like I see on the graphic on the left-hand side, the number hash marks inside here, I'd know exactly what I'm doing, and I'd want to know my colors. You know, what colors am I trying to achieve? Because if I'm using if black is going to be supplied to my stop buttons, then that'll be my standard. By the way, is there any color for control wiring that people are using for a start 3-wire? Is there